Hello, everyone. How's it going? I don't know
It's
why
going well.
I accidentally pinned Heather to the screen. Let me do. Movie pin. There it is. Yeah, my face just got really big.
How are you doing?
All right, not too bad. Having a pretty good time in general. Trying to lose weight, get ready for summer,
Yeah, I feel that.
get my butterboard abs back in shape.
hmm
General stuff.
Yep.
Couldn't get the
That's
screen to
the
go
thing.
small. I'll just use my face. Uh, Everybody healthy? No one's gotten sick, I hope.
I'm supposed to get my first dose of the vaccine this Friday. So.
Oh, good.
Mm.
One of my students had his wife got sick. I could tell he was a little nervous because he ended up emailing me on the wrong day. So, anyways, y'all got to take care of your family and friends and yourself. If you have to miss class, that's okay. Luckily, I record them, so you're not necessarily missing anything. You can always set up a Zoom meeting with me to discuss anything you didn't understand about what was covered in the meeting. If in the Zoom recording. So had a lot of people absent last time. Out of 45 students, I think I only had like 27, 28. It looks like the numbers are going right now for about the same. Our next test is going to be a while from now because our next test covers chapters 10, 11, and 36. The way we do, or the way I do it, is I leave chapter 9. I'm now doing relativity, which is chapter 36. Yeah, 36. I can never remember if it's 36 or 35. And then I'll go back and catch chapters 10 and 11. So I've went ahead and made the practice test available, but you can only, you really can't do anything except for maybe chapter 36 after today. And even then, I think I might actually spend 2 days with it. I'm not sure if I'm going to spend a day or 2 days, depending on what we get done now. I'm not covering all of relativity. I just wanted you to have a good feel for special relativity, what it shows, where it was motivated from, and that sort of thing. So we'll discuss that. Speaking of which, I gotta look up something real quick. I'm looking for, if I remembered correctly, the name of Einstein's paper on special relativity was something like the uh, electrodynamics of continuous media or something weird like that. But anyways, I don't see it immediately, so I can continue waiting for my students to arrive while I look for the name of that paper. Actually, I think I have it in book form right here. It might be easier to just stop doing the internet thing and go to here. Yeah, here it is.
On the electrodynamics of moving bodies.
That's it. Yeah, the electrodynamics of moving bodies. Yeah, it's weird. I mean, because if you think about it, it has almost nothing to do with electricity and magnetism. Yeah, on the electrodynamics of moving bodies, A. Einstein. Yep, that was it. This is a good little cheap book, $4.95. It's actually got his papers, Lorentz's papers, Wales' papers, and Michelson papers, the original papers. So they're not. It's not descriptive. It's not that helpful for people that aren't Einstein or a brilliant physicist. So in that sense, it's not very helpful. But it's good to have the actual original documents. So we're up to 30 people now. So what I want, all right, we're getting more. I got to 31 now. So what I want to talk about is special relativity. And this is that wonderful year in 1905 when Einstein wrote probably enough papers to win him at least 3, if not 5, Nobel Prizes. So in 1905, Einstein was working as a lowly patent clerk, which actually was kind of a good thing for him. He thought it was really nice to not be steeped in academia, where he could just do his job and think about things that he wanted to think about when he wanted to think about them. And specifically, the big thing of the time were people making clocks and stuff like that. So he had a lot of time to think about time in general. And he wrote a paper on the photoelectric effect that did win him the Nobel Prize and was one of the founding papers, the second founding paper of quantum mechanics. He also wrote a paper on Brownian motion, which was explaining how little pollen grains on the surface of a glass of water sort of zigged and zagged back and forth like this. And they do it today. I mean, you can literally just take a glass of water and drop some pollen grains on them, very, very small pollen grains, and you'll see they actually move a little bit. People didn't understand what that was about. They thought it might be actually little animals, and they made the word animalcules, like animalcules, animal molecules. So they call them animalcules. And that was solved by him as well. And basically, in writing that, he ended up solving or basically proving beyond a shadow of doubt that atoms existed. At the time, most people believed atoms existed, but they didn't have concrete proof that they did. Einstein did a statistical analysis that basically either he was right or he just got so lucky as to have won every lottery every day of my life for 70 years, say. That's like the probability of him being wrong and atoms actually not existing, or him being right and atoms not existing. So he definitively proved the existence of atoms. He showed quantum mechanics to exist. He wrote the special theory of relativity, which could have won the Nobel Prize as well. And then, like the next day, he says, "Oh, by the way, I was puddling around in my office and discovered this E equals mc squared," which basically showed how the sun worked. Which by this time, 1905, the historical record was still the book of Genesis. And if you add up the begats from Adam to someone who existed in time from the historical record, which is King Nebuchadnezzar, when you add up those begats and the lifespans that took place until the begat, until a person gave birth, you can actually get the age of the earth or the age of the universe, in fact, according to the book of Genesis. And you get that basically right now it'd probably be around 10,000 years old, somewhere around. I did it once and I can't remember what it was, but basically you expect a couple 6 or 8,000 years before the common era, and then the common era is of course 2000. So that's really where the difference comes in. But that was the historical record, and that was the oldest thing we had. The Old Testament's quite old. It's maybe 4,000 years old. That's a pretty impressive thing. The only thing older is the Epic of Gilgamesh that I know of. Anyways, when you do that and you look at the sun and you take Lord Kelvin's calculation, which basically he said, let's assume the sun is the best burning thing that I've ever discovered, which is coal. And I know its weight. Let's assume that whole thing is a ball of coal, and that's its weight, is the weight of the sun. And he calculated that could probably last 25 to 50,000 years. Well, that's fine. The history of the Earth is only 10,000 years old. We're about at least as small as a half, but up to a quarter of the way across there. So that's not too terribly bad. And it's everything's good. But at the same time, we're starting to get sciences by Lyell from geology and other people that are suggesting that maybe the Earth is hundreds of thousands of years old or even a million years old, right? And if that's the case, you got this big problem of how in the heck could the sun actually last this long? We're also seeing Darwin come along and had his evolution of species. And we know that takes a long, long period of time to evolve from one species to a next. And again, you're coming up with figures that are well over hundreds of thousands of years. So Einstein, in writing E equals mc squared, not only did he, in some sense, what many people would argue, won us the World War, because he was able to basically use that information to create nuclear weapons, which in some sense helped speed up the end of the war. But also, more importantly, in my estimation, is he showed how the sun actually works. E equals mc squared. If you take the mass of 4 protons that goes into a fusion reaction and compare it to the mass of a helium nucleus, which is 2 protons and 2 neutrons, you subtract the difference in those masses and multiply that by c squared, and that's the energy you get out from that reaction. And when you do that, you say, okay, well, how many of those reactions must occur for the total amount of light the sun puts out? That tells you how much mass it burns up per second, and then you multiply that, or you can take and divide the total mass by that, and that'll give you an estimate of how long the sun will live. That calculation comes up a little bit off. It ends up getting by you assuming basically that the entirety of the earth, of the sun can be burnt. You end up getting like I think 35 billion years. But when you correct for it only being maybe 10 to 15% being burnt, then it comes down to about 10 billion years. So all of those things could have actually won Einstein the Nobel Prize, in fact, several times. And in fact, he and his ex-wife were so confident. He was married to a woman that he wanted to divorce. They were not happy anymore. She was a physicist as well, and she was quite bright, and she worked on his theory of relativity with him. They even had a child. They have one child that sort of disappeared, which is kind of an oddity. Einstein goes down in history as this extremely moral and upright person who, for instance, moved to America and, after getting his citizenship, could tell everybody that America was, quote unquote, the greatest country ever. Only it had this one blind spot about race, and he wrote ad nauseum about race, saying this was wrong. And in fact, what inspired it was a black opera singer that came to New Jersey to give an opera, and people didn't realize she was black. When she got there, her hotel wouldn't honor the reservation she had made because she was black. She wasn't allowed to stay there. And Einstein opened his home to her and let her stay there. And so he was compelled to write an article about how bad the racism thing was. So he's this really moral character. But at the same time, we found out he had a kid who had some mental issues. In other words, he was probably mentally handicapped, extremely so, like not able to take care of himself, and he just disappears. So again, that's probably consistent with the things that happened in that time, but it's still completely inconsistent with a person that can see beyond racism and all that stuff. But anyways, when him and his wife are going to break up, he says, well, I don't really have any money. I'm sort of poor. I'm a patent clerk. I just got a job as a professor, and that's not very impressive salary. He said, I really can't offer you anything. And he says, well, how about my Nobel Prize winnings? And she wisely took the bet. He said, well, if you let me go now out of my marriage and not owe you anything, when I win the Nobel Prize, you can have the prize. And she said, yeah, because she knew he was going to win the Nobel Prize. So that's pretty confident and pretty cocky about how cocky and brilliant they both were. So she did end up getting his Nobel Prize winnings. He went on to leave and he toured around. And then when general relativity came in, he really got popular, not only from the scientific community, but from the lay people. In fact, I think I can't remember who wrote his biography most recently. I think it was the same guy that wrote the John Adams biography. McCullough? No, it wasn't David McCullough. Isaacson, maybe Walter Isaacson might have wrote it. But anyways, he wrote it, and he said at one point, right after the general theory of relativity was shown to be correct, at least in that aberration of starlight thing, Einstein had 12 girlfriends. And Jay Leno made the comment, God, 12 girlfriends. How would you keep all that straight? You'd have to be oh yeah, this is Einstein we're talking about. So I'm not saying that's a good thing to have 12 girlfriends. I'm just saying for a dude that looked like that to have 12 girlfriends, somebody must have been impressed because he wasn't all that pretty. All right, so that was Einstein, and what he did was, again, he was thinking about time, but he also knew Maxwell's equations. By this time, I told you Maxwell had died this horrible, sad life at I think the ripe old age of 43 of some horrible stomach cancer, and just like his mother did, in fact. And he died without the respect of his peers, despite being the Lucasian professor of mathematics, which was the same position that Newton held, the same position that Dirac later holds, the same position that Stephen Hawking later holds. He was esteemed in that way, but he had graduated second from the top. He was the second wrangler at Cambridge, and therefore everybody thought he wasn't quite that bright, but he was really, and it was sad that they didn't understand. He had revolutionized electricity and magnetism with 4 equations in vector calculus form, and I think part of it was that vector calculus was such an esoteric branch of mathematics that there might have been, I would say, maybe 100 people worldwide that actually understood that. And probably in some sense, part of it was a lot of people that didn't want to go to that fancy new math to make sense of what he did. But by the time Einstein comes along, Maxwell's equations are perfect and everybody realizes it. And not only are they perfect, they're relativistically correct, meaning they do give you exactly the right results consistent with special relativity. And that's what Einstein was using. That's why he said on the electrodynamics of moving bodies, because what he realized is if you take Maxwell's equations, there's a special thing you can do with the four equations where you put them together and it makes a wave equation. A wave equation has a very specific form in physics. You'll see it. You might see it in this semester, but you'll definitely see it in the next semester. But basically, you got a second order derivative of the amplitude variable with respect to space, a second order derivative of the amplitude variable with respect to time, and then there's a little slot that's the velocity squared in there. And there's no place, like if you switch from one frame to another frame moving with a different velocity, the equation doesn't change at all. And Einstein saw that as a problem because he was doing these thought experiments where, like, if he was riding on a beam of light and went to shave, he like couldn't see his own reflection. And what he came up with was what he considered paradoxes. And paradoxes are not allowed in science. Okay, if you have two ideas that are both consistent with your science as you know it, but contradict one another, then that's a paradox. And he found a lot of them with Maxwell's equations, and therefore he knew something was wrong. And he suspected Maxwell's equations were right, and that was his guide. And ultimately, what he did was came up with the special theory of relativity. And the special theory of relativity has two postulates. I'll let you copy them from the book. I'm going to tell them to you in my own words. You can get them from the book yourself. But the first one is the laws of physics are the same for all inertial observers. Okay, that little caveat, that inertial, is what makes it special relativity as opposed to the general theory of relativity, which means everything. Okay, general. I know that sounds like it's not as important because you think of special as, oh, my special little son, right? Not in the southern way, but in the special little son way that, you know, I'm daddy's boy or I'm mama's boy or whatever, right? So special means only in the special case of inertial circumstances. What do we mean? Well, the law of inertia, which is Galileo's law of inertia, or Newton's first law of motion, says that object in motion tends to stay in that motion unless acted upon by a net external force, and it recognizes that motion as a constant velocity. So neither the speed nor the direction is going to change at all. So if you actually attach a camcorder to a merry-go-round where it can only see the disc of the merry-go-round, and you put a bowl, or let's say a bowling ball or a basketball somewhere near the center of the merry-go-round, and you start filming and someone spins the merry-go-round, you'll see the bowling ball or the basketball, whatever you use, sort of roll out to the center. I mean, out of the center, out to the outside. To you, you don't see any forces acting on it. Again, you're attached to the merry-go-round. The merry-go-round, you don't know if it's rotating or not. All you know is you see nothing acting on it whatsoever. You just see a ball shoot out as if it did not obey the law of inertia because it indeed accelerated. Okay. So what he's saying is anywhere you see something that looks like something accelerating without a force, then that is a non-inertial frame. And the case in point would be that one, as well as an object falling in gravity, because we don't see anything reaching out from the sun to pull the earth towards it. So why assume it's a force, right? So in the case of gravity, he's going to say that's a non-inertial reference frame, and that's a new way of looking at it. He's not the only one looking at it that way, but it's a new way of looking at it, and it ultimately leads him to the general theory of relativity, which corrects gravity as well. So that's what he means by the laws of physics are the same for all inertial observers. In other words, if you don't see a clear thing causing an acceleration, you assume that is not an inertial frame. That was rule one. Now, the rule two is really the weird one. Rule one was the laws of physics are the same for all inertial observers. Rule two is that the speed of light is a constant independent of the motion of the source or the motion of the observer. Okay. Now, me and a friend of mine, when we were in high school, we were riding down Portsmouth Boulevard. just actually, we were riding down Elmhurst Lane and just crossed Portsmouth Boulevard, and my friend Buddy sees a girl that he liked, Mary. She's riding her bike. Well, he's got an idea. He's got a paper out, so he's got a ton of paper bags in his, the bags that we put newspapers in. He's got a ton of those in the back of his car. He goes down, he fills it up with water. He gets in the passenger side, and he's going to ride by and just toss this little bag of water at his friend Mary, who's riding her 10-speed, or it was her beach cruiser, down Elmhurst Lane, and it's just going to hit her and get her wet, and he's going to laugh, and everything's going to be super funny. Well, what he didn't understand is the law of relativity, which basically says, hey, if you're going 30 miles per hour and you drop a 5-pound bag of water out the side of the window, that bag is going to be going 30 miles per hour. So you're basically taking a 30-mile-per-hour swing with a 5-pound hammer and hitting the girl that you're impressed with in the chest. Okay, so it completely knocked her off her bike. I'm sure it bruised the hell out of her, knocked the wind out of her, all sorts of stuff. It was horrible. But he didn't really understand that. And of course, we're like sophomores, maybe freshmen, but I think sophomores in high school. We should have known better than to still hit girls when we're crushing on them, but we didn't. So, anyways, that happened. Well, that's what's going on with relativity. Imagine that that wasn't the case, that you're just riding along in the car and Buddy throws the bag out, and despite the fact you're going 30 miles per hour, the bag goes at the speed that Buddy makes it go. So the bag has a speed of bag, like a speed of light. Then it wouldn't have been any big deal. It would have just been, hit like every other time you hit someone with a bag of water, which obviously is never. But it's still, for argument's sake, that's what we're saying. So it's also as like you're riding on the flatbed of a flatbed Mack truck trailer, going 60 miles per hour, and you're old like me, so you can only throw 60 miles per hour now, and you throw in the direction of the truck. So you're going the same direction as the truck, or the truck's going, say, north, and you're throwing northward from the bed of the truck at 60 miles per hour. If you were able to allow them to travel for a whole hour, you know that the truck would cover a distance of 60 miles in that hour. And then the actual throw would cover an additional 60 miles. So you'd add those two and get 120 miles. And that was done in 1 hour. So the relative speed of the ball with respect to the ground was 120 miles per hour. That's just the addition of velocities rule from Galileo, which we talked about before. Velocity of A, C is equal to velocity of A as seen by B plus velocity of B as seen by C. So 60 plus 60 gives you 120. But what we're saying, if one of those velocities, say the velocity of my throw was C, the speed of light, then the answer would not be 60 plus C, but would just be C. And if I threw it backwards, which in the case of an actual Mack truck going 60 and me throwing it 60 in the opposite direction, you on the side of the road would see the ball just sitting perfectly still and drop straight down. So that'd be zero velocity, because 60 minus 60 is zero. But in the case of the throw speed being the speed of light, it would just be C again. That's the big deal. Okay, so that was his second principle of relativity, the principle of the constancy of the speed of light. And that doesn't matter whether you're the source, which I was moving, or the observer. So if you also run towards the Mack truck at 60 miles per hour, say you're on a death wish, you're going for a head-on collision with a Mack truck, you're driving 60 towards the Mack truck's driving 60 towards you. So that's a net effect of 120 miles per hour. But there's someone on the back throwing a ball at you at 60 miles per hour. Then the net effect is 180 miles per hour. Well, in this case, if the ball was thrown at the speed of light, it would still be just C, not C plus 120. Just C. Okay, so that's the big deal. Now, that is his special theory of relativity, but lo and behold, some of the equations already existed. In fact, there was a series of equations called the Lorentz Equations, Lorentz, and Lorentz happened to be another hero of Einstein's. He was a brilliant mathematician / physicist, and he figured out a way for explaining a really difficult experiment, which I'm going to talk about now. So the Michelson-Morley experiment is the experiment I'm talking about. At this time, as well as Einstein being the only one that realized that there was a target and the only one being able to hit it, some people make the argument that genius is a person that can hit a target that no one else can hit. But another person I read once said the smarter introduction to genius is a genius sees a target that no one else can see and then hits it. And that's really what Einstein did, because no one knew the laws of physics were in error. If you ask people in the late 1800s, early 1900s, the vast majority of scientists said, we figured out science. We're just going to do a bunch of experiments to make sure our laws are right to the third, fourth, fifth decimal place, and we'll be done. So Einstein saw a problem where no one else even saw it, and then he solved it all by himself. And he did it in his brain. He used what's called Gedanken, or thought experiments, to imagine scenarios that he couldn't actually do physically. And then he would use his logic and brilliance to figure out how to make sense of it. And in that way, he basically revolutionized science, both in the special theory of relativity and the general theory of relativity, without an experimental apparatus or any experimental data to suggest it needed to be fixed. So it was really impressive. But in the same time, we have this idea that we know light is coming to us from the sun. We know that Maxwell's equations showed us that light is an electric wave oscillating in one plane, a magnetic wave, a magnetic field oscillating in a perpendicular plane, and both of those are perpendicular to a third dimension, which is the direction in which the velocity or the wave is traveling. That's an electromagnetic wave. That's what light is. That's what gamma rays are, X-rays, ultraviolet, infrared, microwaves, and radio waves are. We know that's hitting us from the sun, reaching us at Earth, because we're not dead. We actually have life. We have sunlight and all that good stuff. And the problem is, they think that waves cannot travel except through a medium. The waves we're used to are like water waves, sound waves. Those all travel through water or atmospheres. So it's reasonable to them that waves can only travel through a medium. And they hypothesized that there existed a ether, and the ether was sort of all permeating everything. So the ether was everywhere. So they wanted to try to detect the ether, and that's what the Michelson-Morley experiment was about. Their idea was, hey, let's shoot a beam of light and let it hit a mirrored surface at a 45-degree angle, so that half of the light will actually bounce off at a 90-degree angle and then bounce off a flat mirror and come back to that. And then the other half will actually go through that mirror and bounce off a mirror in the distance and come back. And you make those two legs, that distance from that 45-degree mirror, exactly the same as the distance to the other mirror. And then when the light bounces back, if they were affected all by the ether, then one will be going slower than the other, because it's been corrected by riding the ether one way and fighting the ether on the way back, not unlike you flying to the West Coast from the East Coast, fighting the jet stream, and then on the way back, riding the jet stream. Okay, so that's the plan. And when you do that, the light should come back. If there's any ether whatsoever, there should be an interference pattern, possibly, meaning because the light arrived back and actually traveled at a slightly slower speed, the number of wavelengths that transpired might not be a whole number. And if they're off by half a wavelength, it'll be no light seen at all, because a wave will hit a trough. If it's off by a multiple of a whole wavelength, there'll be no change whatsoever. It'll just look like the light came back as if nothing happened. So to allow for that possibility, you then twist it at 90-degree angles, do the experiment again, and if you get a difference both times, you can trust that difference is the right one. And when they did that experiment, lo and behold, it was as if there was no ether. The light didn't speed up or slow down when it was going one direction or the other, or after the 90-degree angle. So Lorentz comes around and says, no, the ether's got to exist. There's no way we're going to have light traveling through nothing. So he says it's as if the ether was mechanically squished, was squished when it was going along with it. And here's the formula. And he ended up getting basically the same formulas that later Einstein's going to do. But Einstein gets them for a much more pleasurable reason, based on postulates that make some sense in retrospect, namely the two postulates I said. So that was really how it all came to be. We still have the transformations from the x, y, z, and t coordinate system to the x prime, y prime, z prime, t prime coordinate system, where you might imagine the x-axes are lined up, the y-axes are parallel as well, and the z-axes are parallel as well. But the x prime, y prime, z prime coordinate system is moving with a velocity, say v, relative to the x, y, z, t coordinate system. So that transformation from between those two systems of coordinates is called the Lorentz transformation, and it comes because he actually derived those equations by assuming the ether was compressed and stuff mechanically. So now I'm going to show you how you can use Einstein's principle of relativity to come up with something very interesting called simultaneity, not being uniform, and another thing called time dilation. So let's turn on my document cam. I've only managed to waste 30 minutes of your life with my spiel. I think that spiel gives you the important context and the historical relevance that I would say you need, but perhaps you feel differently. Let's try to get this in good focus. So one scenario is this. Let's imagine, for instance, actually, I'm going to use the example Giancola uses, which is two train cars sitting by each other. Well, I say appearing to sit by each other. Okay. And there's a detector dead center. They're identical train cars. There's a detector dead center. This is a train moving with a velocity v. And then at the exact instant that they get beside each other, a single lightning strike, okay, strikes right here. And because of a wire system, creates a light that's going to flash. But at the same instant, a lightning strikes right here as well in both cars. Okay, so this is position, say, A1 and A2, and this is position B1 and B2. Okay, now this train car is sitting perfectly still, but this one's moving by at a velocity v. I'm going to rewrite this as A1 just so everybody knows. That's A1, that's A2, that's B1, that's B2. I know it's hard to see. Now, if this is the case, and each time this spot is hit by light, it actually, or hit by lightning, it sends out a pulse of light. What you would conclude is, since these lightning bolts hit at the same time, then this detector in the center would see both of them as being simultaneous. So this part says lightning bolts hit simultaneously. Here's Mr. Younger is going to do a really magical trick. I'm going to spell the word simultaneously. There it is, simultaneously. And if I wrote it small enough, y'all have no idea whether I said it right. I spelled it right, but I think I did. So lightning bolts hit simultaneously according to that detector. Okay, simultaneously. Okay, now that seems perfectly normal. But you also might think, well, maybe this one says the lightning bolts hit simultaneously. But no, that's not the case. The reason why this one said it is because the light coming from A1, which I'll mark with this pretty green, hit at the same time as the light coming from B1. That's why it concluded they were simultaneous, because this is in the center of the cart, equidistant from A1 and B1. Well, the same thing happened here. The light shot this way and the light shot this way, but as that happened, the train car was moving this way. So really what happened is this detector said B1 was first hit by lightning. Then B2, then A2 was. Because to it, what it saw was the light from B2 hitting the sensor and the light from A2 not getting there yet. So again, moving it up so you can see what I'm saying here. So that's a really big deal. Due to relativity, notice the speed of light didn't increase in speed because the train car was going this way, nor did it decrease because the train car was going this way. That's why they ended up not reaching dead center. If it had been corrected by the speed of light being added to the velocity of the train car in this case and subtracted from the velocity of the train car in this case, then they would have hit dead center, and both of these guys would agree, both of the detectors would agree that the lightning bolts were simultaneous. But because the velocity of the light did not change just because the source of it, A2 and B2, were moving at velocity V, they rendered them not simultaneous events. So what's simultaneous in one frame is not necessarily simultaneous in another, and that's called the relativistic lack of simultaneity. Okay, that's a big deal. That helps us basically figure out the ladder and the barn paradox we'll talk about later. There's also a twin paradox and a rotating disk paradox. I might get to the rotating disk paradox, but I'll definitely get to the twin and the ladder and the barn paradox. So that's one issue. So simultaneity is not, let's say, universal. It is, here's a neat word, relative. Okay, so it is relative. And your book opens up with Professor Tompkins. Y'all can still order that book if you'd like. It's actually a really good, robust introduction to relativity written by George Gamow, one of the greatest physicists of all times, in that he inspired so many things. My undergraduate advisor actually met him and asked him about the spin of the electron and got a really brilliant explanation of why electrons have spin that he could not remember because Gamow was so smart. But anyways, he's a monumental character that wrote really entertaining books about relativity and other things. So that's one of the ramifications of relativity. So that's one ramification. Another ramification is time dilation. And now let me show you how we're going to do time dilation. And this time I'll use a train car as well. So what I'm going to do is imagine a train car. Like this. Okay. And what's going to happen is we're going to have a very special clock. In order to make use of the second principle of relativity, which is about the speed of light, you've got to have something with light in it or you're not going to be able to make any headway. So Einstein created clocks made by using light. So you could imagine a single beam of light shooting out from here, then hitting a mirror, and then bouncing back. And when this thing, that's also a source and a detector of light, detected the light returning, it would go click, meaning that's like one click of time. Okay. So if you're sitting on this train, okay, and let's say this height right here is distance d, okay, then delta t0, the proper time, this is a time measured by you who happen to be not moving relative to the clock. That will be called the proper time, not to be confused with some kind of absolute or preferred time or anything like that. That's just the time that is measured by someone who does not see the clock moving. Okay, that unit of time will be given by, remember, velocity equals distance divided by time. So time should equal distance divided by velocity. Well, the distance the light traveled in this case, notice the light's going to go up and then it's going to come back down like that. So the distance traveled will be 2d, and the velocity used would be c. Okay. So according to the parked vehicle, the parked train car, and it doesn't really have to be parked. This is actually just occurring to a person inside of it. In reality, the train car is not necessarily parked. It just say, so I'll put quotation marks around it to say this is what the person inside maybe thinks. Now, what actually might be happening is the train car might actually be moving at a velocity v. I'm trying to draw this one lighter and this one lighter because these are future things. And this is like the right now. Okay. So there's our light detector and source. There's our light detector and source in each of the three spots. And here's our light mirror in each of the three spots. Now, according to me, watching this train car go by at a velocity v, here's what transpires. The light beam in this frame will go up and to the right, hitting that mirror, and then it'll go down and to the right, getting back at the sensor. So I think from the Pythagorean theorem, you can see how to find this distance. And in fact, what we'll say is the distance from here to here is actually going to be the velocity of the train times 2 delta t. Okay, because just times delta t, sorry. Because the time delta t is the time that this person on board, or this person off to the side watching it thinks transpired from the beam going up and then back down to returning. Does that make sense? Okay, now I think you can see from that delta t, which should be the total distance traveled, which is, notice this would be v delta t over 2, and this, of course, would be d. So it's a right triangle. So I'm going to say the distance traveled will be 2 times the square root of d squared plus v times delta t over 2 squared, like that. That's the distance traveled. But according to relativity, the velocity is not going to change just because of the motion of the source, so the velocity will still be c. Okay. Now I can take these two equations, which I'll call equation 1 and equation 2, and from equation 2, I'll get 2 prime, which is c is equal to 2 square root d squared plus v squared delta t squared over 4 over delta t. That's going to be equation 2 prime. I'm going to take equation 2 prime and combine it with equation 1. So 2 prime in 1. And that's going to give me delta t 0 is equal to 2d over, now c, of course, is 2 times the square root d squared plus v squared delta t squared over c over 4. Okay, all that over delta t. So this becomes 2d delta t over 2 times the square root d squared plus v squared delta t squared over 4. I think you can see that the 2's cancel out. Okay, now we have d times delta t. I'm going to try to manipulate this and get an expression for delta t in terms of delta t0 or vice versa. So what I've got a delta t0 already solved. Let me see what I can do. I will try to multiply. I will square this thing and then put it inside of the square root. So this will become d squared delta t squared over d squared plus v squared delta t squared over 4. All of that now will be under the square root. And now I can, let's see. Actually, I've chosen a different way. I was trying to work out the algebra to solve it in a different way, and it's not panning out as nicely as I had hoped it would. Let's make this, flip this over and put it in the bottom just to see what happens. So now I'll get 1 over the square root of d squared plus v squared delta t squared over 4. Now that would mean this all becomes the denominator down here, which would be d squared delta t squared, all of it still under the square root.
Can you move it up? It's kind of
Yes.
off page.
Did I run out of screen? So now all that is in the bottom here. Now I can divide through that. I'll get 1 over the square root d squared under 1 under d squared would just be 1 over delta t squared. And then the d squared over here would become v squared over d squared. The delta t squareds would cancel out, but you get a 4 down here in the bottom. So that's not all that pretty. Now I don't want to get a common denominator because that'll get me right back where I started from. I tell you what I'll do is I will pull this over here and I'll say delta t0 times the square root of 1 over delta t squared plus v squared over d squared times 4 again. Yeah, I think I can do this. This is all equal to 1. In other words, when I pulled this over here, I got all this is equal to 1. So if I wanted to get a common denominator, I could do that. I would say delta t0. I think I'm just going to end up right back where I was, but let's see what happens. I'm going to get a square root of, I've got a delta t squared, I got a d squared and a 4 squared here. So what I need to multiply this 1 by is 4 times d squared. And then this denominator would be 4 d squared delta t squared. And then, of course, this one's got the d squared and the 4, so I'd have to multiply it by delta t squared. So this will be plus v squared delta t squared. That's still not very pretty. That's still equal to 1, though. Now, what I'm going to do is multiply by, I don't need that d anymore. That's a problem. Let's try this. Let's scratch this attempt. Let's try squaring c, 2 prime. So let's say 2 prime, and I'll square it. When I square 2 prime, remember 2 prime is just that 2 delta t square root d squared plus v squared delta t squared over 4. When I square that, I'm going to get c squared is equal to 4 times d squared plus 1/4 v squared delta t squared over delta t squared. Okay, so now I've got an expression involving c squared. Thinking more along the big picture, knowing what I want versus what I have a delta t0 in terms of d. Maybe, just maybe, it would be smart for me to solve for d squared here, or solve for d, so that I can put it in there. So I'm going to try that. Now I'm going to get c squared delta t squared is equal to 4d squared plus v squared delta t squared. So notice I just distributed that 4 in here, and I multiplied by t squared on both sides. That got it over to there. That's why I got that now. And then distributing that, the 4 hit the d squared to make 4d squared. But the 4 hit 1/4 v squared delta t squared just to get v squared delta t squared. So that works out pretty nicely. Now I can take that and say 4 d squared is equal to c squared delta t squared minus v squared delta t squared. Or you could say that it's actually equal to c squared minus v squared times delta t squared. Finally, we can say that d is equal to the square root of c squared minus v squared times delta t over 2. Notice what I did here. I divided by 4. That would give me c squared minus v squared delta t squared over 4. Then I took the square root of both sides. The c squared minus v squared stays under the square root. The delta t squared, when you take the square root of that, you just get delta t. And the 4, when you take the square root of that, you get d. So now I can try to plug this in 1. I'm going to call this equation 3. And I'm going to say 3 in 1. That should give me delta t0 equals 2d over c. So I'll write 2 over c, and then I'll write d, which is the square root of 1/2. So I'm making this d over here into just 1/2. And then I'm taking the square root of c squared minus v squared times delta t. And I think you can see that the 2 and the 1/2 clearly cancels out. And the c, I can pull that inside of the square root and it'll become squared, but it'll be in the denominator. So I get square root of c squared over c squared is just 1, and v squared over c squared is just v over c quantity squared. And then I have delta t. So finally, I can say that delta t is equal to delta t0 over the square root of 1 minus v squared over c squared. That is the result. That is time dilation. Okay. If you notice, if you consider the case, let's say v squared over c squared equals 3/4. So v squared over c squared equals 3/4. 1 minus 3/4 would be 1/4. The square root of 1/4 would be 1/2. So 1/2 in the denominator is 2 in the numerator. So this factor, 1 over the square root of 1 minus v squared over c squared, is actually bigger than 1. So I'm really multiplying the time that the person on the train car, the proper time, measured by a number greater than 1. That means what the person in the train car thought was 1 second, you on the side of the track is going to say is 2 seconds long. Does that make sense? So that's time dilation. That's our ultimate equation. Let me write it here in terms of some things we know. So the time delta t is equal to the proper time delta t0 over the square root of 1 minus v over c quantity squared. Now, we often make some abbreviations that make life easy. For instance, there is something called gamma that is 1 over the square root of 1 minus v squared over c squared. In other words, it's this thing that's being multiplied by delta t, so or by delta t0. So what that means is if I use that, I can just say delta t is equal to gamma delta t0. Something else we also use is v over c is defined to be beta. So you can also say that gamma is equal to 1 over the square root of 1 minus beta squared. So those are some abbreviations that make your life a lot easier when you're trying to write this stuff. Beta just represents V over C. So just now I imagined a case where V over C is equal to the square root of 3/4, because then when you squared it, it became 3/4. So V over C, which is beta, is equal to the square root of 3/4, which is actually the square root of 3/2, which I think you all know is 0.866. That's 86.6% of the speed of light. And that implies gamma is equal to 2. So that's a factor of 2 that the time dilation will be adjusted by. So let's imagine an experiment. Let's imagine that we've discovered this one ice cream from Dairy Queen is the perfect ice cream, okay? But this perfect ice cream from Dairy Queen is made such that it's consistently able to melt in exactly the right amount of time to exactly the right level. So let's say this ice cream from Dairy Queen takes exactly 10 minutes to melt from a full ice cream to a pool of liquid that's level on the top of the cone, okay? So if you are on this train traveling at 0.866 times the speed of light, 86.6% of the speed of light, you would record that time as taking 10 minutes. So you hold this ice cream maybe over a bucket and you just sit there and watch it. And sure enough, you come back in 10 minutes. It's basically a liquid level with the top of the sugar cone. Okay. Now you have a friend that's sitting on the side of the track who's watched you using a telescope when you were a really far distance away. He watched you have the full ice cream and he started his timer, and then he watched you, and just as that ice cream melted down to the level with the top of the cone, he was you were passing him on the railroad tracks, and he stopped his stopwatch and said, "Wow, that took 20 minutes." That's really what happened. We know this for a fact. We have done it with the Concorde. We have flown a cesium clock in the Concorde around planet Earth, and we knew how fast the Concorde would go during the path, and we corrected for that. And lo and behold, when it got back, the cesium clock that we had left at the airport changed from the one on the Concorde by exactly the amount that Einstein's theory of relativity predicted. Okay, so moving clocks move slower, meaning the second hand goes slower, the hour hand goes slower, the minute hand goes slower, meaning your heart beats slower. And here's the weird part. If you had a telescope watching your friend on the side, and you used your telescope and you looked at the instant you were a long 10-minute ride away on your 86.6% of the speed of light train car, if you looked through a telescope at your friend, like I said, 10 minutes earlier, you would see his actual ice cream cone being full height. And then as you rode 10 minutes, you would see your ice cream come to a melt, and then you'd look at him as you're passing him, and you'd see his is only about halfway done. And then when you make the full 20-minute ride, you look back and say, oh, his is finally there. So his to you took 20 minutes. And there's no right answer. They're both right. That's what makes it relativity, because there's no experiment you can do to tell which one's actually moving, right? Accelerometers can detect acceleration, but they can't detect velocity. If you're in an aircraft and it's not a lot of turbulence, and if it was quiet enough where you couldn't hear the engine, you couldn't really tell whether you're moving or not. And that's sort of the big deal. So relative velocities are a really relative thing. So according to you, the person that was watching you, your friend, is actually moving this way at 86.6% of the speed of light, whereas your friend thought you were moving this way at 86.6% of the speed of light. And both of you are correct. Only thing that matters is when you're solving problems, you stay in one reference frame, or you have to correct for being into moving to the other reference frame. So you both agree that the other person's ice cream took 20 minutes to melt, even though you both agree your own ice cream took 10 minutes to melt. The other expression is time dilation. In that case, we find that length is equal to the proper length divided by gamma. And this is length contraction. And basically, we're saying that moving objects shrink. Oh, shrink. I don't know why I put a D there. Parallel to their motion. So a Lincoln Continental, which was a big long car that we used to use for cop cars, they would be very long, but if they travel at 86% of the speed of light, instead of being, say, 12 feet long, now they're going to be 6 feet long. However, if you're in the Lincoln Continental and you see another Lincoln Continental going by you at 86.6% of the speed of light, you will say your Lincoln Continental is 12 feet long and his is 6 feet long. Okay. And the proper length in this case is the length measured by someone who doesn't see the length moving. So again, it's not moving. Something's not moving. That's what we refer to as proper length. All right. Another one's mass. You end up getting the exact same expression for proper mass. The mass is equal to the proper mass divided or times gamma. So mass actually increases as well. That's one way of looking at it. I don't believe in ascribing that one because mass is a scalar. It's not supposed to change. But that's one way of looking at it, because at the end of the day, when you actually go, you use F equals ma, which does work, by the way. F equals ma becomes a problem because the faster you go, the larger your apparent mass gets. I should say F equals dPdt works. F equals ma, not so much. But that causes something that's like mass increasing. And that gives us a good explanation of why nothing can travel at the speed of light, because it would take an infinite amount of energy. If it has any mass other than zero, it would take an infinite amount of energy and an infinite amount of force to make it reach a velocity of the speed of light. All right, we finished the three main result for the four main results of relativity, specifically time dilation, length contraction, lack of simultaneity, and something that looks like increasing mass or mass dilation. We haven't done it all, so I will cover next time another the rest of chapter 36, but you can get a lot of the physics problems done. You can look at a lot of examples in your textbook and get those done. You can do the practice test, at least the chapter 36 part. And you can get started on your homework. So we're done for the day. You guys are free to go, but you're also free to stick around. If you have any questions, I'll wait for the last person to leave.
Have a good week,
Mr. Gamer.
You too. Have a good weekend, or a good rest of the day anyways.
Have a good one. Stay safe.
Mr.
Thank
Gamer.
you. Yes, Rowan. All right, let's see.
Yeah.
Did someone have a question?
According to the online homework, it says the chapter 36 stuff is due tomorrow. I don't know if that's actually intentional.
No, that's not. I'm going to change that right now.
Okay, because I already did the first part of the 2 parts for the chapter 36 homework.
Oh,
and
good
because
job.
we hadn't actually covered it in class yet, I only got like a 60 on it. But
Are you still allowed to do it again to improve the score? Or
no, because
If I
I've already
moved it-
gone through all the questions for it. I haven't done part 2 yet, so hopefully I'll do better on that one, especially if you actually extend the time.
would you like me to reset that first set so you can just start it anew? I mean, you'd have to do it again, but you could get a higher grade.
Nah, I don't think so. I think I'll just accept that I got low on that one because I
Okay.
got really high. I got like 150 on the one you gave extra credits to.
Oh, cool. You're good.
Yeah. I was just
Well, I'll set
slightly
both of those
confused on that.
dates to probably at least Sunday. I might set one, maybe the conceptual one to Sunday, and the first one to Sunday, but the second set I'll set to Wednesday of next week.
Yeah, because I was looking at that. I was like, why are we doing chapter 36 stuff? I could swear we didn't actually cover that in lecture yet.
Oh, no, we did. You were just, now you were sleeping, man. That's what happened.
Oh, no.
No, I'm messing with you. So yeah, no, I will. I'm definitely going to change that. And like I said, if you want to consider redoing it, I will gladly change it. But I certainly understand not wanting to do the work again.
Yeah. Okay. I just wanted to point that out.
Thanks, Rowan. Appreciate it, bud. Anybody else have a question? Campbell, or excuse me, Vanessa, Lauren, you got
So you're
one, Lauren?
saying that you're changing the conceptual and chapter 36 homework dates?
Yeah, I think I'll move the conceptual and the first part of 36 homework due Sunday, and the second part I'll make it due Wednesday.
And also, I had a question from like the practice test.
Yeah, go for it.
One of the, I just want to make sure that if that's not a mistake or not. But one of the questions from the, well, this one is really worded. In fact, yeah, I have to share the screen.
Okay, go for it. Anybody else have any questions while we're waiting for Lauren to pull that up? All right, go for it, Lauren, whenever you get it up there.
Trying to find it.
Hey, buddy, what's going on? Look at these. You hungry? You hungry?
Take this attempt to, yeah. Give me a second. I'm trying to find it.
No
For some
problem.
reason, not. And then
No one else. I think no one else has a question besides you, so it's fine. I don't even think they're necessarily there. So go for it.
Here it is. It was question 4.
Okay. So yeah, the elastic collision is actually where the kinetic energy is conserved. That's the definition of an elastic collision. Total energy is always conserved, period. So that's why you'd say that's false. It's a weird question because you know for a fact that total energy is conserved, so you want to say true, but in fact they're asking specifically about the term elastic collision, which just means kinetic energy is conserved.
Right. Wait, explain it again one more time.
Okay, so it's asking collisions in which total energy is conserved are said to be elastic collisions. That's way bigger than the statement of what an elastic collision is. An elastic collision is just a collision in which the kinetic energy is conserved. But it's also a weaker statement in the sense that all collisions require conservation of energy, period. We've never found anything that violates conservation of energy. So that's just nature. So really the answer should be false because an elastic collision just means kinetic energy is conserved, not total energy.
So the elastic energy conserved, not the total energy conserved.
Not the elastic energy, the kinetic energy. The energy,
kinetic energy.
Yeah, 1/2 mv squared is conserved for an elastic collision. That's the definition of one.
So if it would have said total kinetic energy, then it would be true?
Yes.
Okay.
It makes sense. I know it's kind of weird, like I said, because of the total energy. But remember, total energy is always conserved. It's just a matter of can we track down all the individual sources.
Okay. And
Anything else?
yeah, in the MATLAB homework. It was like one of the questions in the MATLAB homework. It
Mhm.
was like you have to find the collision angle, I think.
That should be a chapter 9 homework. Yeah. Collision at an angle. There you go.
Yeah, there's one. Yeah, I'm just confused how that really came up.
Okay, so two cars, both of mass m, collide and stick together. That's what we call a perfectly inelastic collision. For the record, by the way, prior to the collision, one car had been traveling north at speed 2v, while the second car traveling at speed v at angle theta, or excuse me, angle phi, south of east. Okay, I see south of east. As indicated in the figure, after the collision, the two-car system travels at speed v final at angle theta east of north. Find the speed v final of the cars joined. Let me write this down real quick before you take away the screen. I'm going to write down the information and then show you how to solve it. Okay, now I'm ready. So I'm going to go ahead and give me the screen back, and I'll show you, see if we can figure out how to do that. So what we have here is momentum before the collision is equal to the momentum after the collision. That's a vector quantity. So the momentum in the x direction gives us the following. So P sub x gives us the following. Initially, this thing doesn't have any x momentum at all. If I call this, say, the x-axis and this the y-axis. So initially, the only thing that has a x component of velocity at all is the velocity, the vehicle right here. And its velocity is v times the cosine of phi. So we say its momentum is mv cosine phi. That's before the collision. And then after the collision, we get m, or I'll just call it 2m because the vehicles are stuck together. So this will be 2m times v final. Now, in this case, this is the angle. So the x component would actually be sine of theta. So that's the expression we have for v final in terms of phi and theta from the x component. Now, for the y component, what we have is the velocity initially for this vehicle is 2mv, but the velocity initially in the y direction for this one is negative mv. And in this case, it's times the sine of phi. So that's the initial kinetic energy, or the initial potential, or dang it, I keep saying energy. The initial momentum in the y direction. It's 2mv for this one going up, and then it's negative mv sine phi, because this one's going downward. After the collision, it becomes 2m v final times, now I need the y component, which would be cosine theta. So that's my figures. Notice the m's all cancel out, so I can go ahead and get rid of the m's. And what I'm trying to solve for ultimately is just plain V final. And I want to look for a way to do that. It looks like if I
So the 2m, so the 2m time velocity final for the first one, the x vector, that's the x vector of the vehicle going up on the y-axis, right?
Yeah, this one, right? So instinctively, what I'm wanting to do is divide one equation by the other, and that'll end up getting rid of V final in terms of tangent of theta. What was the answer in terms of that they gave us for V final? Can you tell me what it actually was? I
V
remember
over
there's.
two,
Go ahead.
V over 2 to the square root of 5 subtract 4 sine. What's that? What do you call that? Weird
Theta.
theta. It's not theta, but it's like the circle with a
The
longer
phi.
line through.
Oh, phi.
Yeah, 5.
Okay, so I had it in terms of phi, and there's no theta in it, no 0 with the horizontal line.
No.
So they're wanting us to eliminate theta completely. Okay, so I'm thinking now what we want to do is square both equations and add them. So for instance, if let's call this equation 1, let's call this equation 2, 1 squared is going to be V squared cosine squared phi is equal to 4V final squared sine squared theta. And then equation 2, when I square that, I'm going to get 4V squared minus 2 times 2 minus 4V squared. The 2V going to be V squared times 2 times the sine of theta, or excuse me, times the sine of phi, plus V squared sine squared phi is equal to 4V final squared cosine squared theta. So now I can say add the two equations. So 1 squared plus 2 squared gives me V squared cosine squared phi plus 4V squared minus 4V squared sine phi plus V squared sine squared phi is equal to 4V final squared times sine squared theta plus cosine squared theta. In other words, I went ahead and factored out the sine squared or the 4V final squared from this one and this one, mainly because I knew this quantity was just 1, and now I've completely gotten rid of theta. At this point, I can start combining like terms. I think you see cosine squared minus sine squared can be one of them. Actually, cosine squared plus sine squared. Yeah, so I've got V squared is going to be in all of them. So I will say V squared cosine squared phi plus 4 squared plus 4 minus 4 sine phi plus sine squared phi is equal to 4V final squared. So now I can see cosine squared plus sine squared. That those two just add up to give me 1. So I can say V squared times 1 plus 4 is 5 minus 4 sine phi.
Hey, scroll down some, please.
Oh, sorry. Thank you. Is equal to 4V final squared. So now I think you can see where it happened. V final has got to be 1/4. So this would be 5/4 minus sine phi square root times v. I think that might be what you had, or maybe you have this with a fraction or something else like that, but that should be roughly it.
Okay. But I'm just still kind of thrown off on how you found the x vector for the vehicle that's going up only on the y direction.
Okay, it's not only going on the y direction, it's actually going in the x and the y direction. Oh, you mean this one?
Yes.
Okay, so this one had no momentum in the y direction. That's why it's not in there at all.
What is the set?
Excuse me, it has no x dimension, no x momentum. That's why it's not in there at all. It does have a y dimension, and that's all of it. It's 2 times m times v, which is that one right there.
What is the v cosine phi equal to?
Okay,
Whose
so remember
vector is that?
momentum is a vector quantity. So momentum p is equal to mass times velocity. Now, if I want momentum x, then I take m times v, that would be the magnitude of it. And in this case, that magnitude is this right here, and it makes a right triangle. The y component is negative. Notice it has to point down, and it would be times the sine of phi, which is why I have a negative mv sine phi. The x component, on the other hand, is here, and that's a cosine of phi, and it's in the positive direction. So that's why I have a positive mv cosine phi here. So it's just straight vector stuff. You've got to be able to convert your vectors into x and y components. And you can't just blindly always say that the cosine of the angle gives you x component and the sine of the angle gives you the y component. You always have to work out the triangle.
I do understand that. I'm just trying to figure out, like, I understand how you found cosine phi. I'm just confused how you found two final sine theta, unless it's that from the vector in quadrant 1.
It's this, okay, for this one right here. So the two vehicles stuck together. So now their mass in the P equals mv formula is 2m. Two cars stuck together of mass m each have a total mass of 2m times v final in vector form would be the total final momentum. So that's why the 2m v final is there. But if you want the x component, you have to take the sine of theta to get that. So the 2m, the 2 comes from the fact that the two cars are stuck together.
Okay.
Does that make sense?
Yes, yeah, somewhat.
Yeah, you just got to remember when things, when two masses stick together, the new mass is m1 plus m2. In this case, both of them were m, so m plus m gives you 2m. Might have not helped that I wrote the m so badly here. Maybe that's better now.
So it's TV final cosine theta. That's the y component of the vehicle in quadrant 2.
You mean this one, mv cosine phi?
No, the other one,
Oh,
the one written in black ink at number 2.
okay.
And
Okay,
the
yeah. So,
and the y component is 2v final cosine theta. Is that the y component of the vehicle in quadrant 2?
it's the total combined when the two are stuck together. They're moving off with this velocity. The only thing is different is this one I divided out the masses because the m was common to all three terms. So it's literally this without the m's in it. So 2v minus v sine phi equals 2v final cosine theta.
Okay, so they're the vectors of the vehicle. I mean, of the final velocity in quadrant 1. That vector in quadrant 1 represents the vehicles together.
Yeah, the vehicles stick together and move off in quadrant 1. That's correct.
Okay, that kind of makes sense now. All right.
All right.
Yes. Thank you.
Keep it up. You just got to practice, man. One day it's going to click and you're going to feel a lot better. All right. See you, Lauren. Have a good one. Rosa, you still don't have any questions, right? I don't think she's there.